In the stock room, where we keep our chemical stock, we often have stock solutions. These are solutions stored in concentrated form. One of the nice things about solutions is that it's very easy to measure out a certain number of moles of the solute. You don't have to get out your calculator and calculate it and use the balance and weigh something out. All you need is a graduated cylinder and a very short calculation, and you can figure out how many milliliters of it to take to get the right number of moles. And so solutions are really convenient. So in the stock room, we tend to have stock solutions, and these are pretty concentrated, and then we take those and we dilute them. And this reminds me of going to the grocery store and buying frozen orange juice concentrate, right? And really, where there's oranges all over the place, why would you do that? But, you know, people in the rest of the country aren't so privileged. So you buy the orange juice concentrate. Why do they sell it frozen in the concentrate instead of freezing a whole gallon of orange juice? Well, it takes up a lot less space, which means when they're shipping it all over the place, it's less expensive. And storing it in the grocery store, storing it in your freezer at home is more convenient. And it's also, you know, if you had a whole gallon of frozen orange juice, you'd have to wait a long time for that to thaw out, right? And so the smaller one, you're mixing it with water, and that helps it melt a little faster. So this whole idea of diluting solutions is very much like making orange juice from that concentrated orange juice solution. So what do you do to that can of orange juice concentrate to make it drinkable? You add water, right? So when we take a stock solution that's concentrated and we need to dilute it, we just take a certain amount of that stock solution and we add water to it, just like you're making orange juice. So we do have an equation here that helps us to understand the relationship between these two. So here we've got M, that's a capital M, that's the molarity of the first solution times its volume is equal to the molarity of the second solution times its volume. So let's think about this for a minute. Capital M means moles per liter. If we multiply that by a volume in liters, what unit do we get? Moles. So what this is saying is that the moles of the first solution is equal to the moles of the second solution. Think about that orange juice concentrate. Okay, it's got some amount of orange goodness in it, right? When you put it in the pitcher and you add more water, have you changed the amount of orange goodness? No. The amount of solute doesn't change. Only the volume of the solution changes. Because the volume of the solution changes, the concentration changes, but the actual number of moles of solute that you have in there do not change. Does that make sense? Orange goodness does not appear or disappear when you add water to it. Okay? So that's why this equation works. M1V1 equals M2V2. I like this better than some books talk about dilute and concentrated. It doesn't matter which one you call 1 and 2. As long as you keep the concentration with the volume of that solution and don't swap the volumes or something. I think this is very important. This equation applies only to solution dilution, and that rhymes on it, solution dilution, not to stoichiometry. Sometimes people try to use this for stoichiometry calculations. And what's tricky about it is that if all of your coefficients are 1, it works. But is that the case all the time? No. So let's not get into the habit of using something that only works sometimes. So we're only going to use this for dilution. Just a lab safety note. When you're diluting acids, you always add the concentrated acid to the water never the other way around. You never add water to the concentrated solution. The reason for this is that when you mix a concentrated acid with water, it generates heat. It's an exothermic reaction. If you put a little bit of water into the acid, it can sometimes generate enough heat that it actually causes it to boil. And when that happens, bad things happen. This actually happened at a different community college several years ago. A student stockroom worker was making a large quantity of sulfuric acid. And instead of adding the concentrated sulfuric acid to the water, he had one of those big 4-liter graduated cylinders, and he added water to the graduated cylinder full of concentrated sulfuric acid. It got very hot, and the graduated cylinder, being narrow, acted like a cannon, and it erupted out the top, and there was concentrated sulfuric acid dripping off the ceiling of the stockroom. It was a major thing. Hazmat came, and the police department and the fire department and incident reports had to be filed. The student was okay. The student was wearing a lab coat, and he was wearing his safety glasses. And he did get some chemical burns, but he went and used the safety shower, and he did recover fully. So that was really important. You know, he at least was wearing his safety protection, and so he was okay. But that's just, you know, a local example of you need to be careful with this stuff. One of the ways you can help yourself remember this is a lot of people around here have swimming pools. And if you don't do it yourself, you've probably seen someone do it, where you need to add acid to the swimming pool, right? That's the concentrated acid being added to the large swimming pool. That's the correct direction. It's not pouring the swimming pool water into the bottle of the acid. So if that helps you to remember. It's like pouring acid into a swimming pool. You always put the concentrated thing into the larger dilute solution. It helps to dissipate the heat and avoids bad accidents. Okay, so let's do some calculations here. How much 6 molar sodium nitrate solution should you use to make 0.585 liters of a 1.2 molar sodium nitrate solution? And these resemble the gas laws a little bit, right, with the 1s and the 2s. Excuse me. You know, I actually haven't done this before, but let's try the whole table thing. Because here we're given 2 molarities. That's our tip-off that this is dilution. So let's try making a table just like we did, because M1V1 equals M2V2 sounds a lot like P1V1 equals P2V2, right? Boyle's law. So let's make a table here to help us organize, 1 and 2. First number we come to, 6.0 molar. Is that a molarity or a volume? Molarity. That's kind of a giveaway because it's got an M on it, right? How much should you use to make 0.585 liters of a 1.2 molar solution? Do you see these 2 numbers are tied together in the sentence? We don't want to take this volume and stick it up here. This one goes with that one. I don't care if you call it 1 or 2, that doesn't matter. But they both need to be the same. So we've got 585 liters, and the concentration that goes with that is 1.2 molar. This is our volume column. So what are we looking for? Volume, V1. The dilution equation is M1 V1 equals M2 V2. Thankfully there's no fractions in there, so we can just set to rearranging it right away. V1 is what we're trying to find. So we divide by M1 on both sides, and those cancel out. The thing about the units with this sort of a calculation If these two units are the same, we're good. If these two units are the same, we're good. It doesn't matter exactly what they are. If this was milliliters, it would still be fine. Our volume that we calculate would just be in milliliters. So V1 will equal molarity 2 times volume 2 divided by molarity 1. So 1.2 molar times 0.585 liters divided by 6.0 molar. 1.2 times 0.585 divided by 6. I'm getting volume 1 equal to 0.117 liters. How many significant figures should that have? 2. So we're going to round this to 0.18 liters. Thank you. Wow. I did that just to test you. You're all awake. This is good. My test worked. 0.12. And does this make sense? This one's more concentrated, and this one's more dilute. So we're going to have a frozen arrow. There we go. This one, large volume with the smaller concentration, smaller volume with the larger concentration. Any questions? When we're making a solution by diluting it, this procedure is assuming that this is not an acid. I disagree a little bit with their illustrations here. They're saying first add 0.625 liters of the concentrated solution and then dilute with water. Okay, this is KCl. It's not going to cause a problem here. But I think it's always better to put some water in there first, put some solvent in there first, then add the concentrated solution, mix it around, and then dilute to the mark, and then stopper and invert. With the doing with the solid, I would also put water in there first, because it's very rare for your volumetric flask to be bone dry. Can you imagine trying to dry the inside of one of those with a long skinny neck? I know students are very creative with paper towels, but you can't do it. There are ways you could do it using solvents and blow dryers and stuff, but usually we don't do that. It doesn't matter. But I don't want my solid going in there with just a little tiny bit of water. I would much rather have it about half full of my solvent and then add either the solid or the concentrated solution. So that's a little beef I have with the author.